So we talked about dynamic viscosity, we talked about kinematic viscosity, and we made a small historical excursion to Stokes. Now we're going to ask a practical question about how we would measure the viscosity of a very dense fluid, which is of biological origin, honey. In order to measure something, we need an instrument. The instrument we will assume that we have used is a ball drop viscometer, and the measurement is then therefore called viscometry. Now this is a theory course, so I'm going to give you some numbers and I expect you to try to solve this and arrive at an answer. It's a test of your understanding of theory, and indeed in a laboratory you would normally conduct this experiment to validate this theory, to check whether this number is real. So the first thing that I have given you is something we derived, as you recall, in the theory lectures, which is the dynamic viscosity eta is equal to 2 by 9 into the difference between density of object and density of fluid times acceleration due to gravity times squared radius of the ball drop upon v term. V term is nothing but the terminal velocity. If you recall, the idea of the ball drop viscometer is a simple one. There is a ball that we allow to fall through a column of fluid. This is typically some kind of a cylinder. We also assume that the length of the cylinder is long enough that the velocity at some point reaches a terminal velocity and it does not change when the upward and downward forces are equated, and therefore there's no acceleration. That was the derivation. So when we now allow this ball to fall through the fluid, we use a stopwatch, measure the time it takes to travel through some distance L prime, and use velocity is equal to L prime by T, and this velocity is the terminal velocity so long as it's not changing. So that's what I meant by terminal velocity. So let's just look at this equation and ask ourselves, what are the terms that we have and what do we need? G is a constant, it's gravitational acceleration. If we use a ball of a known size, we know it's R. The density of the ball is something we can measure, weight per unit volume. The density of the fluid also we can measure, its weight per unit volume. And V term is part of the experiment. So in a way we know everything, this is a constant. Okay. So let's put some numbers there. The radius of the ball is 5 millimeters, which is 5 into 10 to the power minus 3 meters. We're converting to SI units. V velocity, as it was measured by some people in experiment, is 0.09 meters per second. You could say 9 centimeters per second. This is our terminal velocity. And delta rho is the difference between the density of the object and density of the fluid. So let's calculate this. What is the density of steel? It's a steel ball, like ball bearings. This is 7.8 grams per centimeter cube. You can find this on many engineering and physics textbook constant pages. Converting that to kg per meter cube gives us 7.8 into 10 to the power plus 3. That is 7,800 kg per meter cube. Density of the fluid is, for honey has been reported to be 1.4 kg per liter. We want to convert from liter to meter cube. In order to do that, we refer to our standard idea. 1 ml is 1 cc, as it's sometimes called, cubic centimeter. Therefore, 10 to the power 3 ml is 10 to the power 3 centimeter cube, cc. 10 to the power 3 ml is 1000 ml, which is 1 liter. 1 liter is 10 to the power 3 cm cube. But cm to meter cube is 10 to the power minus 2 into 3, that is minus 6. Therefore, 3 minus 6. Therefore, we end up with minus 3. Okay. So, with this in hand, we can convert our kg per liter to kg per meter cube. So now that we have the two density values for steel, we have in terms of kg per meter cube 7,800, and for honey we have 1,400 kg per meter cube. So now we are in a position to substitute all the values. So eta becomes 2 by 9 into the difference between 7,800 minus 1,400 multiplied by g, which is acceleration due to gravitation, 9.8 meters per second square, multiplied by r whole squared, which is 5 millimeters radius, which is 5 into 10 to the power minus 3 meters whole squared, upon 0.09 meters per second. And if you do the calculations, you get 3.871 Pascal second. Now, something that I have not mentioned before, that is a very useful trick, which is sometimes called order of magnitude estimates. Which is to say, how do we know this answer is correct? So we can look at our numbers. 2 by 9 is roughly 1 by 10, which is 0.1, 10 to the power minus 1. The difference between the densities is 7,000 minus 1,000, which is about 6,000. So that becomes 10 to the power 3, and 6 rounding off is 10. 9.8 meters per second square is 10. 5 into 10 to the power minus 3 is 10 to the power minus 6, and 25, which we will take as 10. And 0.09 meters per second is approximately 0.1 meters per second, which is 10 to the power minus 1. And when we take the orders together, we end up with minus 1 plus 3 plus 1 plus 1 minus 6 plus 1. So minus 1 plus 1 goes, plus 1 becomes 2. So all this adds up to 3 minus 6 is minus 3, plus 2, 3 minus 6 minus 3 plus 2 is minus 1. Now it looks like we may have missed something, but this could be attributed to the exact values that we have taken. Something like 10 to the power 0 is what we were expecting. This may have something to do with some of the approximations in the denominator that we took. So we got a 10-fold lower value than expected. Such orders of magnitude estimates are very good quick checks that our numbers are not wrong, but the basic check over here is, of course, do it in a calculator and check again. For comparison, the viscosity of water is 10 to the power minus 3 Pascal second, which means that honey is 3,000 times more viscous. That is a huge number. So what of it? So some of the questions that we can ask now is that, of course, honey also depends on the source. So depending on which flower, which bee collects it, from honeybee to honeybee, from beehive to beehive, we may find different numbers. In fact, the viscosity of honey can be used as a qualitative measure of honey. So this is a biotechnologically important measure because, as you know, honey can be adulterated, made synthetically using sugar solutions, and physical constants like this can help us measure things. What about the viscosity of cytoplasm? We are in a biophysics course. You might actually want to know what is the viscosity of cytoplasm. Well, the answer to that question is a bit complicated because we know while the cytoplasm is 70% water, there are also DNA, proteins, ribosomes, small molecules. In prokaryotes, no organelles, no intracellular membranes, but in eukaryotes, also membranes. So all these structures are likely to affect the measure of viscosity. And in this context, we're going to come to this topic later about how crowded the cell is and whether this affects the viscosity. So I just want you to keep in mind that the viscosity of a cytoplasm is a complex measure. There is a lot to it, and you can intuit a certain number, but these numbers may be off due to reasons of physiology. So in this case, I've taken a bacterial cell and a representative view. And I just want to remind you that macromolecular crowding might be an aspect that we will need to consider. So for the last topic, I'm going to talk about viscoelasticity of cells.